I would like to thank you for coming to this talk, which I am sure it will not be as entertaining as the talk that, or as a movie that my governor, the governor of the state of California, can give you. I would like to thank the International Union of Material Research Societies for the 2007 SOMIya Award for Professor Brunserade and myself. Especially, I would like to thank the people that have been influential in our life and let us work late nights, which are our wives, my wife, Jacqueline, and Ivan Brunserade's wife, Miriam. As you can see, we already started celebrating this 2 years ago. This collaboration between Professor Brunserade from Belgium and myself is a worldwide collaboration. It's a collaboration that starts in the farthest part in the state of California in San Diego, all the way to Belgium, where Professor Brunserade is located at the Catholic University in Belgium. But in addition to just having a collaboration between the two continents, which is the American continent and the European continent, in addition to that, we have a collaboration with the South American continent, with a bunch of people at the Catholic University in Santiago de Chile. So we have been able to complete completely the circle. In addition to that, there have been many other collaborations within Europe that we have had, including Germany, Spain, and France, and many other places. When I first met Professor Brunserade, the impression that I got about Professor Brunserade that he was a very distinguished sort of a man, and this is something that comes out from my blackboard. One day I came into the lab, and one of my graduate students at that moment had written down this thing on the blackboard that says, "Ivan, call immediately Prince Hirade." Now, I didn't know any Prince Hirade, so I was wondering what this is, and the only Prince Hirade that I could think of is somebody in the Eastern Island, which turns out to be in Chile. This is the so-called Rapa Nui. Now, it turns out that after much thinking that we gave it, we realized that actually Prince Hirade referred to somebody that does act and probably looked to me in my first contacts with him as a real prince, Professor Brunserade. And that was the mistake. There is Professor Brunserade, there is Prince Hirade side by side. Now, that was my impression of Professor Brunserade the first. I'm sure that his impression about me was completely different. So this is taken from the museum, from the Roman Museum in Cologne, which is very close to Leuven, where Professor Brunserade is located. And this is some kind of a statue, of a Roman statue that says that the stern of a ship carved on a funeral monument, a beard on the stern indicates that the sailor was a barbarian. And I'm sure that Professor Brunserade had the following impression about me. So here I was, one of the first times that I met Professor Brunserade. I was coming from skiing in France. And I went to a very fancy restaurant with Professor Brunserade dressed with my skiing jacket. So he must have thought that I was a real barbarian. And so all I have to do is to ask him for forgiveness at this moment. So the physics glue, however, that these two different people that we were so different and so with such a different backgrounds, historical backgrounds, there was something that glued us together, and this was the physics. And what I will tell you about today is about several physics glues that glued that together. Metallic superlattices was the first one many years ago. Low and high TC superconductors, vortex physics. These are the things that glued us together. Now, it is very easy to come up, actually, in some sense, to come up with ideas of how you would like to be glued together through physics. However, this is not possible without the funding agencies that allowed us to work together. And we are very fortunate that we had funding for this from NATO, which no longer actually funds this kind of collaborations, unfortunately. The Flemish Academy, the Catholic University, and a bunch of funding agencies, both in the US and in Europe. Now, the most important thing, actually, of all this is our collaborators. We had a bunch of junior collaborators, both at UCSD, at Argonne National Labs, where I was before, and in Belgium. We also had some long-term collaborations in Belgium, in France, in Chile, in Spain, even in Sweden. So these are all our collaborators. And I would like to say that this collaboration, this international collaboration, has not only been an international collaboration that permitted us to do a lot of work together and publish a lot of papers and come up with a lot of inventions, but in addition to that, we had a lot of effect in the students and postdocs that worked with us. So both from this collaboration, the students and the postdocs that worked with us have ended up going all over the world. And as you can see, we had an effect in spreading the word about this all over the world, even in Asia, in Europe, in South America, the US, and so on. So here is the plan of this talk. What I will do is I will give you an introduction, and I will give you some history about how this whole work that we did together started. I will tell you about characterization of these materials that we do, the so-called SUPREX program. And since the work that we have done is extremely broad and lots of different areas of science that we have worked on, it will be impossible for me to cover all of the work in a simple talk like this. So what I decided to do is to choose 3 different areas. And I must tell you that this was done in collaboration with Professor Brunserade, who was an integral part in the preparation of this whole talk. I will tell you about metallic superlattices, and there I will tell you specifically about the giant magnetoresistance and roughness. I will tell you about low and high TC superconductors, specifically about dimensional transitions. I will tell you about vortex physics, collective pinning, and then hopefully I'll tell you a little bit about the future. So why do all this? I mean, all this basically can be categorized in a variety of reasons of why to do this. And again, I cannot cover all this area, but what I will focus is on basically on what happens if you make 3 layers of 2 similar materials, a blue material and another blue material, and you separate them with a red material. And there is 2 kinds of effects that you can think of it. You can have effects which are due to the fact that these layers are somehow coupled, that there is a communication between those 2 layers, and there is an effect of dimensional transitions, which I will explain in just a second what it is. So what I will concentrate is on basically on telling you about these 3 layers. I will not tell you about the rest of the thing, just briefly touch on it. And in particular, I will start by telling you about the so-called giant magnetoresistance effect, which has become very popular in the last 15 or 20 years and has given rise to a lot of applications in the area mostly of data storage. So the history of this goes like this, more or less. Many years ago, I started working on magnetotransport in superlattices, and I published a paper a long time ago in the beginning, so to speak, in 1979 in this conference in Hawaii. Unfortunately, it was not a very much read conference proceedings, but in that conference proceeding, I published this paper. I will not tell you the details of that paper, but it was on transport properties of the compositional and modulated alloy copper and nickel. It turns out that this paper had not very much attention from people, but we published this paper in which we measured the magnetoresistance as a function of magnetic field of these metallic superlattices, and what we found there in these metallic superlattices that the conclusion of this was that the magnetoresistance shows an anomalous behavior. Now this anomalous behavior that we found was the fact that we found a very large magnetoresistance of about 17%, which typically for metals the magnetoresistance is less than 1 or 2%. So this was like kind of a major thing, that the magnetoresistance was so large, which has basically left it on at this point. And at this moment is when Professor Brunserade and I started interacting. He actually read some of my papers, which were based on a conference actually that I organized. And he read this paper on artificial superlattices. And then at some meeting in Lake Geneva, so it's Lake Geneva actually in the US, although Professor Brunserade spent some time near Lake Geneva in Switzerland. So this is even historically sort of an interesting fact. And here it is what came out of this work. At that moment, this article appeared in the Discover magazine, and I decided to go back for the purposes of this talk, to see what did we say in this Discover magazine article about the work on metallic superlattices, and these are the kind of things that we said. We said things like, superlattices may lead to a new breed of electronic devices, metal superlattices for using computer memories. In 4 or 5 years, this will be the field in material science. And it turns out that actually many of these things are not so stupid, and they have been fulfilled, since nowadays in every of your computers, this type of phenomena, which have to do with the magnetoresistance of these multi-layered metallic elements is used in every computer nowadays. So metallic superlattices originally started, and this is what was the first motivation for our interaction, was we started wondering what happens to the magnetic, superconducting, elastic properties of these kind of materials if you make a layer of an orange material and a blue material, and you put them on top of each other and you repeat them many ways. These are the so-called metallic superlattices. Now, it turns out that after many years of this, we evolved to this very complementary laboratory. So here it is a laboratory. Here is the MBE laboratory that is in Professor Brunzerade's lab. This is an ultra vacuum system where there is lots of different metallic systems can be prepared. This also led very recently, actually this is an MBE system in my lab, made for organic materials now. And this is a laboratory, a clean room laboratory that we have in this building at UCSD, the so-called California Institute of Telecommunications and Information Technology, IT2, which led to all these. And these are the type of instrumentation that we use for preparing this kind of materials. Now, the question that you have to ask immediately is, are expensive instruments sufficient to assure the structure of the materials? Whatever we conceive, is this expensive instrument sufficient for this? And so, of course, the only way to assure that is to look at the material once it's prepared. I mean, one may have all these facilities, but in fact, it is not clear that just by having these facilities, it is sufficient in order to be able to assure what one wants to have, that is what one has there. So therefore, one should worry about the structure of the materials. Now, you may want to ask, why care about the structure at all? Why not just make these materials and maybe they'll have interesting properties? Well, the reason that you want to care about the structure is the following, is that, first of all, there is a postulate in solid-state physics or in material science, is that the properties of a solid are given by the atomic locations. It turns out that if you look at these materials in particular, small structural changes lead to large effects on the physical properties. For instance, to give an example, 2% expansion in the lattice, so if you slightly strain the lattice, 2% only can give rise to as much as 100% change in elastic constants. So this is a very important issue, is to worry about what the structure of the material is, and how does that affect the physical properties? And so once, actually, we discovered this big magnetoresistance, actually, we started wondering about what happens at the interfaces of these materials. Remember, we are just putting down a few atoms. And so we have to characterize quantitatively at the atomic scale. And this is more or less the point at which we started interacting. We met at Lake Geneva. We discussed about it, and eventually I ended up going to Leuven to spend a few months there working in Professor Brunzerade's lab. And so remember what I did, what I told you initially, that the type of materials that we think that we're working on are these orange and blue materials. Nowadays, notice that this is all colored by hand because this was in the times where PowerPoint and all these fancy computer things that we're using today didn't exist. And notice that here I draw a perfectly layered material and without any kind of interdiffusion, nothing happening there between the blue and the orange materials. Now, it turns out that the question is precisely that. We conceive this in our mind. The question is this the way that the thing really looks like? Well, in fact, it turns out that as soon as you start thinking about this, you immediately realize that this is not how things look like. That probably what happens at the interface there is the interfaces are not perfectly flat. There is all this roughness, there is interdiffusion, there is all kind of issues that you have to deal with, and all these different type of property changes at the interfaces between these materials will affect the properties quite substantially. So because to characterize these materials quantitatively, then one does what is called a scattering, and it's one of the key methods for this is called a scattering. In particular, X-ray scattering is what we do. And what I want to show you here is that the X-ray scattering, you have to remember that the X-ray scattering, what it measures is the intensity of the X-rays, which is not more than the square of the structure factor. So it's the product of the structure factor times its complex conjugate. And this actually gives you information about structural, chemical, magnetic properties of the interface there. Now, it turns out that there is a problem with this, and the problem to this is a well-known problem, which is that the phase is lost because you take a product of the structure factor times its complex conjugate, then the phase is lost. And because the phase is lost, it is not possible to take directly the intensity and invert directly the structure and get the structure directly. That is not possible. So one needs to do what is called a refinement. And this is well known for bulk materials. We actually developed jointly refinement, which is 14 films. This now is downloadable actually from my website directly. It's in its 10th reincarnation. And this was a real collaboration between two groups. Professor Brunserade had a student, Hans van der Straten. I had another student, Eric Fullerton. And these two guys worked independently in each one of the lab. We didn't tell each other that we were working on this problem. And a year after they worked on this, we put them together to check each other's results. And this led to this development of this program, the SuperX program, which now there is many installations all over the world using this software. And if you are interested in this kind of materials, you're welcome to download it. It's free. There's very few things in the world is free. Well, actually, it's not completely free. You have to give us a reference, but it doesn't cost any money. And here it is some example of that. Here it is a metal. So here it is the example of a molybdenum nickel metallic superlattices. The circles here are the data. The thin line is what a perfect material would look like. And there it is, the perfect material. So this is, again, intensity as a function of 2 theta X-ray diffraction. And you don't have to be Einstein for this. I mean, basically, you can tell that the data does not agree with the calculation for a perfect material. What this refinement does for you, this SuperX refinement, is basically fits the data. And insofar that how well this data fits, this tells you something about the characteristics of this interface. Notice here that this is on a logarithmic scale. So therefore, the small changes that you see here are really small. It's 1 part in 100. It's a very small change. So therefore, this is a very, very, very good fit. And this tells us something about the interdiffusion, about the roughness, about the expansions at the interface, many of the properties that we would like to know. Now, this, years after, it's expanded to many other areas. For instance, this is in oxide superconductors, high TC superconductors, YBCO and presidium BCO. Again, the experimental data, the perfect superlattice doesn't fit. The refinement fits it quite well. It went to semiconductors. These are some semiconductors, indium arsenide, gallium antimonide, which are used for infrared detectors. These are very recent work. Actually, it's just very recently been published, where we can tell something about what happens at that interface between the indium arsenide and the gallium antimonide, what happens to that interfacial layer, how to optimize these structures. Even very recently, we have some unpublished work in which this same kind of technique was utilized to characterize what are called metallo-phthalocyanins, which are some kind of organic superlattices. So this has become very successful, and this was one of the hallmarks of this interaction between Professor Brunzerade's group and my group. And as I'm telling you, there was many graduate students and even undergraduate students that have worked on this subject. Now, I'll go back a little bit about the properties of the physical properties of those materials, the transport and roughness in magnetic superlattices. This turns out to be very crucial for this giant magnetoresistance effect. So, so what I will tell you is about some work that we did that started actually with a paper several years ago, like 15 years ago by now, in which, again, it was a collaboration between the two groups. And this eventually led to a bunch of other works in my lab, actually, in addition to that, with many other collaborators from all over the world, from South America, from Spain, and many other places. And so, so what is this giant magnetoresistance? So this giant magnetoresistance is what I alluded to at the beginning, is this change in the resistance with magnetic field. Now I will tell you about iron-chromium superlattices. Basically, what this is the following, is that if you have an iron layer, which are these magnetic layers here, that are separated by these chromium layers, and you have 2 types of electrons that have the spin to the left, or to the right there, and the electrons that have to your left, I guess, and here are the electrons that are to your right. It turns out that if all the electrons are, all the magnetic moments point in the same directions, then the ones that are to your right there, they are able to go through here easily. However, the ones that are pointing to the left, they bounce against these red spins of the material that are pointing in the wrong direction. Now, this is the situation if you're in a high magnetic field pointing towards the right. If you're in a zero magnetic field, in a low magnetic field, where it turns out that these materials have this strange property that they order in antiferromagnetic layers. So the spin in one layer points to the right, the other spin points to the left, the other spin points to the right. In this case, whether you have electrons pointing to the right or electrons pointing to the left, they both bounce. One of them bounces against this layer, the other ones bounce against that layer. And as a consequence, this magnetoresistance is high, this magnetoresistance is low. This was actually found out in iron-chromium superlattices by the group of Professor Firth. And so again, in this anti-parallel resistance, in this situation, the magnetoresistance is large. In this situation, the magnetoresistance is low. So that's how the magnetoresistance looks like. And so basically what we did is we did an experiment in which we varied again the roughness, we prepared these materials in a variety of different ways, and we studied the way the magnetoresistance changes with all these properties. And what we found is, here it is the key of this here is the plot of the magnetoresistance as a function of roughness, that basically this scales with roughness. So the magnetoresistance scales with the roughness. What this tells you is that there is a lot of interactions at the interface, and most of the effect comes from the interfaces. So the conclusions are, of course, in the papers, and then I won't tell you more about that. So now I want to tell you about dimensional transition in low and high TC superconductors. This started in some work in which we compared both what happens in low temperature superconductors, what happens in high temperature superconductors. And here it is, for instance, one study that we started with the transition temperature as a function of thickness of these individual layers. And as you're making the layers thinner and thinner and thinner, what happens is that the transition temperature decreases. And it decreases because of either because of proximity with other things that are around there, or because there is a dimensional change, because the material goes from being three-dimensional to being two-dimensional. This leads to another interesting thing, that if you measure the critical field, the superconducting critical field as a function of temperature, in a region in which there are three layers which are coupled strongly together, the material looks three-dimensional, so therefore the dependence of this quantity is linear, like this. However, if you separate these layers enormously by some other material in between, then the dependence becomes square root-like, so becomes two-dimensional-like, which is like this. And this effect was observed in a bunch of extensive studies that we did, where you go from three-dimensional behavior to two-dimensional behavior. This in particular for lead germanium superlattices, which was done again in collaboration between the two groups. So then we did many other works in a variety of different combinations, and I don't have the time to tell you about the details of all this, but basically all this relates to this fact that in high temperature you have this three-dimensional behavior, at low temperature you have this two-dimensional behavior, and there's a transition from 3D to 2D. So as a function of temperature, now you can have a transition between 3 dimensions to 2 dimensions. Now, the last thing that I will tell you is about collective pinning in superconductors using magnetic nanostructures. And this one comes from the following consideration. This is what is called a vortex. And this actually became very popular. In fact, just a few months ago, well, 2 months ago, I had to cancel a trip to Cancun because one of these vortices, one of these hurricanes, Hurricane Dean, came to Cancun, and they had to cancel the international. In fact, this was the International Union of Material Research Society had a conference, sponsored conference there. So this is a vortex in the sky. This vortex actually can be had also in a superconductor, so where electrons instead of the air moving around, and that's how a supercurrent looks like. So there is a supercurrent in a superconductor. You have these vortices. These electrons are whizzing around. Because of that, there is a magnetic field in the middle of it, what is called a flux line lattice. And this happens in type 2 superconductors in a certain field range. So that's how the phase diagram looks like. There's magnetic field versus temperature. In this region, there is the so-called mixed state. And in this mixed state, what happens is that these vortices interact strongly with each other. As these vortices interact, because of the repulsive interaction, they form a lattice. You see, if you look very closely here, you will see that there is like a hexagonal lattice there. The thing orders itself into little triangles. And this is what is called a flux line lattice. Now, you can actually look at the topography of the film, and you don't see basically anything there. However, if you look with a magnetic force microscope, then you can see these vortices. And here is an example of it. There it is a vortex, there it is a vortex, 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 vortex. So that is the triangular lattice of vortices. This is for niobium, which was actually, this material was made in my lab and then sent to Brunserades' lab. And as you can see, there is many interesting things that we investigated. We investigated where these vortices locate themselves using this magnetic force microscopy. But again, I don't have the time to tell you about the details of it. But suffice it to say is that we are able to identify where the vortices are. We're able to identify what their size is, what their location is, how they order, and so on. Now, in a niobium, we have imaged this also in a niobium film, and we actually have looked at the magnetic field profile and all kind of detailed things. Now, this is in isolated vortices for the moment, what I'm showing you, and we both did this for niobium, and we also did it for high-temperature superconductors like YBCO, and I'll show you an example of that in just a second. So we have studied where these vortices locate compared to the topography of the sample, and so on. And so these are the results. I mean, again, I don't have the time to get into the details of all these, but this has led to quite a bit of work just to look at these single vortices in either in a low-Tc superconductor or a high-Tc superconductor. Now, the interesting thing is what happens if you take the material, the superconductor, like a niobium, and you drill holes in it, for instance. So this was actually known, for instance, for a while, that this phenomena, but Professor Bunserad and his group actually revived this whole field. So there is a lead film with holes in it. If you measure the magnetization of this lead field as a function of field, you see a curve that looks like this. However, if you drill holes in it, instead of seeing a curve that looks like this, the curve looks like this, see? This. And it turns out that each one of these kinks here are related to the situation in which there is either one vortex entering into each one of the holes, or two vortices entering into each one of the holes, or three vortices. So there is some kind of a matching effect between the lattice of the artificially drilled holes in there and the vortex lattice. Now, I picked up on this. Professor Bunserad, this group actually looked at this, and I found this very interesting when I heard from him about it. And so I picked up of it, and I wondered what happens if one, instead of drilling holes, one makes small magnetic dots. And this has led to this work in my group, where we made some small magnetic dots. So here there are some small nickel dots on a square array. And then what you do is you stick them in there, the array, and then you have a niobium film there, and you put a current, and again measure the voltage. And again, I don't have the time to get into the details of this, but one of the interesting things that happens that the resistance this time, not the magnetization, but the resistance as a function of magnetic field, instead of being a smooth curve, like you would expect, it has all these kinks. And these here are huge kinks, they're huge effects, factors of 10, factors of 100. And these kinks, there's many kinks. The separation of these kinks also has something to do with this matching between the vortex lattice and the artificial array of dots. Well, so for instance, there's up to 8 order peaks. You can tell, again, many of these effects are very interesting, and you don't really have to be extremely knowledgeable in order to realize that something interesting is going on there. So now, very recently, actually, just as of, even this year, we published, after many, many years of Professor Bunserad and I interacting, we started wondering about how come there are many of these problems in publications in physics. And then out of this came out 2 articles, one in English, which was actually published by the MRS Bulletin in 2005, and one that was just published, appeared in the magazine of the Spanish Royal Society in Spanish, where we have set out the so-called rules for how do you tell if some science is not correct and that it's pathological. I can't get into the details of this, but you can read about these articles either in the Material Science Bulletin, or if you want to read it in Spanish. I'm not sure that I'll have it in other languages, but that's about probably it. How to judge science and how to tell that science is wrong. And this came out of this interaction between Bunserad and I, and we were wondering, how come things that we find that are wrong, other people cannot find that are wrong? And so that's why this led to these 2 articles. And here are the 13 rules. This was done in collaboration with Professor José Vicent from Madrid, from the Universidad Complutense, where I tend to spend quite a bit of time, and I can't get into the details of this, but you can read about it in the Material Research Society Bulletin or in the Journal of the Spanish Royal Society. So, this leads me to the end, that after more than 25 years that we worked together, and after more than 75 papers, I started wondering, what is the secret for a lasting collaboration? Again, here it is the prince, dressed like a prince. Here it is me, an American professor, dressed like a slob. And I was wondering, how come with these different backgrounds, we still had this very lasting scientific collaboration for many, many years. And it is unusual, actually. I've been told many times that 2 physicists standing each other for more than 25 years is actually totally unusual. Well, the reason is, of course, that this physics is great. We are having interesting discussions. We meet interesting people, interesting places. Very recently, we in fact organized a symposium at the last MRS Bulletin on integrated nanosensors. So I have to say this is very important, but it's not the only thing. And you can't forget something even perhaps more important, which is you have to enjoy each other's company. And we have enjoyed, certainly Bruce Rad and I have enjoyed each other's company in many places in the world. This is in Cancun with Professor Vicente and my wife. And this is in San Diego. This is somewhere in Europe, in the Mediterranean. The company and enjoying the friendship of each other is the most important thing. As you can see, we really can have a good time. And that's probably one of the important keys to having a successful collaboration. So thank you for your attention. And I hope next time I'll be able to be present and give the talk in person. Thank you.